The final project we'll make here will have voxel terrain generation, threaded chunk loading and unloading, block breaking, and block placing. I've linked 2 GitHub repos in the description. One is a Minecraft clone I made previously that has more interesting terrain generation and more block types. The other is the exact code that I'll be writing in this tutorial, which is much more streamlined, but it lacks some of that additional polish to save time. I will also have either video chapters or timestamps in a pinned comment if there's a particular part of the tutorial that you are most interested in. We're going to start by making a new 3D scene. This is going to be one chunk in the world map. We're going to take this spatial node and change its type to a static body. This way the chunk will have collision. We want to attach a script to this. I'm going to rename it first. We can remove the boilerplate code, and we're going to make it a tool so that it updates in the editor. First, I'm going to copy paste in this list of vertices. These are all the vertices that define a cube. There are 8 of them for the 8 corners in a cube. Next, I'm going to define the faces of a cube. I'm also copy pasting these in. So these 4 values in the array are the 4 indices of the vertices array that make up that face. So the top face is made up of this second vertex, the third one, the 6th, and the 7th one. Next, for the chunk, we're going to want an array of block data for all of the blocks in it. We're also going to want a few things for creating the mesh. So the surface tool allows us to create a mesh, which we assign to this mesh object, and then to have it appear in the actual game, we assign that mesh to this mesh instance. We are also going to want to create a singleton script. So I'm going to create a new script called global, and we're going to have some information in here that's going to be useful throughout the project. For now, all I'm going to include is a dimension value, which will be the size of a single chunk. So we're going to make that 16 by 64 by 16. Now to make this a singleton, we go into project settings autoload, we select the global script, and we add it. So now we can use this dimension value in our other scripts. Back to the chunk, we are going to make an update function that will update the mesh of the chunk whenever we need to. We're going to start by unloading the chunk if it's already loaded in. To do this, I'm using call deferred and then queue free. This keeps it thread safe because we're going to use threading for our world loading. And then we just set the mesh instance pointer to be null. Now to actually load, we first want to create our mesh. So we make a new mesh, we make a new mesh instance, and we set up our surface tool to begin making a mesh using primitive triangles. Next, we're going to loop through our entire chunk using that dimension constant we created in our global script. And then here I'm calling a function that we haven't created yet. That's going to be create block, which will handle creating the mesh for that specific block. Next, we're going to do a few things with the surface tool. First, we're going to generate surface normals. Next, we are going to commit our surface tool changes to our mesh. Then we are going to set our mesh instance to have that mesh in it. Then we add that mesh instance as a child of our chunk static body. And finally, we create the tri-mesh collision for it. Now we can start on writing the create block function. And this takes in an XYZ position for the block. Once again, I'm going to call a function that we haven't created yet, which will be create face, which will take in one of these lists of indices up here that define a face, as well as the XYZ coordinate of the face. And we're going to call this 6 times for the 6 faces of a cube, and we're going to use each one of those arrays that we defined up top. Now we have to write the create face function. So this takes in the indices XYZ. First, we want to define the location of every single corner of this face, and we're doing this in global coordinates. So first we get a vector from our XYZ. This will be an offset that we're going to apply to the vertices, and again we're using the indices defined in top, bottom, left, or right to get the location of each corner. Then with these values we are going to add triangles using our surface tool. So a square can be made out of 2 triangles. So the first one is triangle ABC, then the second one will be triangle ACD, and that will create the entire square. One final thing is we have to include our ready method, and be sure to call update the second the chunk is loaded in, and this will ensure that the mesh is created. If we close our chunk and reload it, we now see that there is a plain chunk here. Next, we want to actually have different block types, and we want actual textures on this. You might notice that I've already created an assets folder in here where I've put in this .dds texture that I've created, which is just some simple 16 by 16 textures. Let's make sure that filter is turned off so that the textures don't blur into one another. And we're going to use these 4 16 by 16 sprites to make a few different block types. We're going to go back to our global script. In here, first we are going to define a constant for the texture atlas size, and this corresponds to the size of this image. We can see it is 3 by 2 texture tiles, so that is the texture size. Next, I'm going to define some enums, which will be useful for getting information about different block types. So here we have some keywords, which is going to allow us to define the top texture or the bottom texture of a specific block, and we also have a keyword for if that block is going to be solid or if it's going to be transparent. Next, I'm also going to put some enums for different block types. In this tutorial, we're going to have an air block, a dirt block, a grass block, and a stone block. Finally, we're going to make a dictionary of our block types. So for this, the dictionary key will be the block type enums that we've defined here, and then each one of these, the value will be another dictionary, which will use these enums up here to define certain things about the block. So for the air block, we don't need to know the textures because it's going to be completely transparent. It is not solid. I'm going to copy paste in the dirt block. So if we look at this, you can see I'm using the top, bottom, left, right, front, back enums to define where the texture will be found for that face. So you can see for the dirt block, all the faces are the same. They use the same texture, which is this one in the top right corner at 2, 0 as its vector location. However, using this, we can also have blocks that have different textures for their different faces. So the grass block, you can see the top is defined as 0, 0, that's this one. Bottom is 2, 0, same as the dirt, that one. And then all the other sides are 1, 0, which is this one. And now for the stone block, similarly to the dirt block, it is all one texture for all the sides. Now we have to update our chunk script so that it actually takes into account the material. Before we do this, we're going to have to actually create a material resource. So we're going to create a new resource here. We will make an atlas texture. You can call it new atlas texture, that's fine. And for its atlas value here, which is currently empty, we'll just drag in the texture that we have already created. Now we're going to create another resource. This will be a spatial material. We will leave it with the default name. This spatial material for the albedo texture, we will take our texture atlas resource and slot it in there. Now in the chunk script, we want to preload the material. So that is the new spatial material. Next, we're going to add a line to our ready function. For the DDS texture that we've used for our atlas texture, Godot's import doesn't save that you have turned the filter off, so it keeps turning filter back on. So we just add a line here to take the material, take its albedo texture, and set flags to turns the filter off. Next, we want to create a new function that will set this block data array that we've created in order to tell the game what block it should render at what location. So first, we are going to loop through all of our blocks, and we are going to reset the block array and then resize it first in the X dimension. We loop through the X dimension, size it in the Y dimension, loop through in the Y dimension, size it in the Z dimension. Finally, when we loop through the Z dimension, we are going to want to set the value in blocks. By default, we can make the block into air. Then for simplicity's sake, we're going to base it off of the height. So if the height is less than 16, we will set the block to be stone. If it is less than 32, we can set the block to be dirt. If it is equal to 32, we can set the block to be grass. And then we just have to update the blocks array to contain this block. Then we have to make sure that this new function is being called in ready before we update the mesh. Now down in the update function, firstly we have to set the material on the surface tool, so we can just add this in here. This way our mesh will actually have a texture. And now we have to update our block function to take into account the new block types. Now if I demonstrate something here, is if we look at the chunk right now, if we go inside it, we see there's a lot of faces inside it that don't need to be rendered. So something that we're going to add is a new function that will check if a given block is transparent, and then in our create block function, we will only create the faces if the block that face is looking into is transparent. If it's solid, we don't need to render the face. So first in transparent, we are going to check if the X, Y, Z coordinate is within bounds. If it is, it's going to check if the block is transparent. So you can access into our types dictionary, And the block that we're going to use as the key is the block at the XYZ coordinate in our blocks array. And then we are going to access the solid value using the global.solid keyword. Otherwise, if it is out of bounds, we're going to return true so that we see blocks along chunk boundaries. Now we have to update the create block function. First, we're going to get the block type at that coordinate. If that block is an air block, then we don't need to render a mesh at all. There's nothing there. Next, we are going to update how we're creating the faces. We are going to use our checks transparent method. So we see here that before creating the top face, we're going to check the block above the block we're creating. And if that block is transparent, then we will render the top face, otherwise we won't. And we will do similarly for all the other faces. We are also going to change how the create face function works. We're going to want it to take in a texture atlas offset, which will give it the coordinate in the texture file that it should look to get the texture for that block. And we're going to get this by grabbing the block info from our global.types dictionary using the block type that we have for that block. And then when we pass that in as an argument, we're going to take the block info and we will use global.top to get the texture of the top face, and then it would be global.bottom for the bottom face, etc. I'm going to copy paste in the rest of these calls. So we can see for left, we're looking at x minus 1, right is x plus 1, back is z minus 1, front z plus 1. Now we're going to update our create face function so that it takes into account the texture. Firstly, for calculating UVs of the texture, we don't use a number. In this case, the texture atlas offset is a number between 0 to 2. We need it to be normalized. So in order to do that, we divide it by the texture atlas size, which we have already put in our global script. So now this value is normalized. We also want to get the width and height of an individual texture. This also has to be normalized. So for the height, we do that as 1.0 divided by the y part of the texture atlas size, and then for the width we do similarly but with the x. Now we need the UV locations that correspond to these 4 corners of the mesh. I'm going to copy paste those in. So we see similarly we first move by the UV offset so that we are at the top corner of that texture. Then UVA, this is the top left corner. UVB, this will be the bottom left corner. UVC, bottom right corner. UVD, top right corner. Now we have to update the triangles that we're creating so that we are also including these UV corners. And again, like before, the first triangle is ABC, so it's UVA, UVB, UVC, and then ACD is UV, ACD as well. With this in, if we reload our chunk scene, we now see a texture on all the sides like we defined. From 0 to 16 it's stone, 16 to 32 it's dirt with grass on the top, and if we zoom inside it, we see no unnecessary faces being drawn. Now that we have the chunk working, we're going to create a new scene which is going to be the entire gameplay world. For now, we will just instance a single chunk as a child of it, and we're going to create another scene, which is going to be our player. This part of the tutorial is going to be a really basic first-person controller, so if you already know how to do this, feel free to skip to the timestamp on the screen. So we are going to make our player as a kinematic body. We're going to give it a mesh instance so we can visualize where it is, and we are going to use a cylinder mesh for this. We're going to resize the cylinder so that its diameter is 1, so it is as wide as one of our blocks are. Next, we're going to add another child node. This is going to be a collision shape, and we're going to give it the same shape as the mesh instance. So a cylinder with a radius of 0.5. Next, I'm going to add a spatial node near the top of the player. This is going to be the head. We're going to use this for rotating the camera, which we are going to add as a child of the head. And with that in place, we can start writing our player script. In order to control our player, we're going to need to put some inputs. So we go to Settings, Input Map, and we're going to need forward, backward, left, right. We are also going to want to be able to jump. And while we're not going to code this now, we'll put it in while we're here. We're going to have a button for placing blocks and a button for breaking blocks. Forward, we'll set to WASD for these standard controls. Jump will be space, as you would expect. Placing blocks will map to the right mouse button, and breaking blocks we will map to the left mouse button. We're also going to add a pause button, which will be bound to escape. Now, back in our player script, we will remove the boilerplate. We're going to want to grab our head and our camera. We're going to want to keep track of the camera's rotation around the x-axis. We'll see why that's necessary later. We're going to define a few constants for the mouse movement, which will allow us to look around the screen, as well as the movement speed with the WASD keys, the force of gravity, and the instantaneous velocity that the player is going to get when you press the jump button. Speaking of velocity, we want to track the player's velocity, and we're going to track whether or not the game is paused. When the game's paused, we're going to allow the player's mouse to move freely, otherwise the mouse will be captured to the screen. Now we need our ready function. When the player loads in for the first time, we're going to capture the mouse using the set mouse mode function on input. Next, we're going to create our input function, which takes in an event by default. First, we're going to track whether or not the game is being paused. So when they press escape, we flip the value of paused, and like I said before, if the game is paused, we make the mouse mode be visible, meaning the player can move their mouse around the screen, else we capture the mouse. If the game is paused, we don't need to check any more inputs, so we return. Otherwise, if the event that has been detected is a mouse motion event, we are going to rotate the head around the y-axis. So this is looking to the left and to the right, and we are going to scale the relative X movement of the mouse by the mouse sensitivity. We're going to do similarly for the rotation around the x-axis, that is to say looking up and down, except it's going to be slightly more complicated because we don't want to allow the player to look above 90 degrees or below 90 degrees so that they can't look up and behind themselves. So we're going to track how much we're going to change the x rotation by. Then if that value is going to keep our camera x rotation within the -90 to +90 range, then we will rotate the camera. So we use that to rotate around the x-axis, and we're sure to record that change in the camera x rotation variable. Next, we're going to define some physics processes using the physics process function, and of course, if the game is paused, we return immediately. Now, when we move the player in the XYZ direction, when they're pressing WASD, we don't want that to be relative to the global transform basis, but instead to the basis vector that their head is pointing in. So we grab that basis. Now we want to record the direction that their inputs are telling them to go in. So we set up an empty vector3. If they are pressing the forward button, we want their direction to go into the -z direction from their basis. By default, or by convention, I think -z is sort of the default forward direction in Godot. If they're going backwards, we obviously go in the opposite direction, and then to strafe left and right, we use the x component of the basis vector. After that's done, we can update the velocity of the player in the xz plane based off of their direction vector and their movement speed. We're ignoring the y direction for now because that's going to be where we will perform our jumping. So if the jump button is pressed and if the player is on the floor, this is a default function for kinematic bodies, then we set the y velocity immediately to be our jump velocity we defined earlier. Then we are sure to apply gravity so that the player doesn't just fly off into the air. And finally, we use move and slide to apply the velocity, and we say that the up direction is the normal to the floor, which allows the game to figure out if it's on the floor or not. And then we set velocity equal to what move and slide returns so that our momentum is conserved between frames. We save the player scene, go back to our world scene, and we add a child as and we add the player as a child scene, move the player up here, and now if we try to run the game, we have to select a scene that will be the world scene, and now with it loaded in, you can see we can walk around in 3 dimensions. We're colliding with the chunk, and if we jump off into the abyss, we fall. Now we want to make the world more interesting, so instead of having one single chunk, we will delete that, and we will instead attach a new node, will be a spatial node, and we will call it chunks. And this is going to contain all of the chunks that are currently loaded in the map as its children. And we will attach a script to the world object. I just realized that since I had been using the assets folder to create textures and such, it's been saving everything in here. That's obviously unnecessary. I'll just move them out. First, we're going to want to preload the chunk scene so that we can instance some chunks later. We're going to add a load radius variable, which is going to be the area around the player that chunks are loaded in. So for now it's going to be a 5x5 square around the player. We're also going to want to grab the children of the world, so that is the chunks node and the player node. And finally, our terrain generation is going to be done on a separate thread, so we're going to create a new thread that we're going to call load thread that'll handle that. Now in our ready function, we are going to initialize the chunks. So we're going to loop through that square, that 5x5 square here, and at each point we're going to instance a new chunk scene. We're going to call a method that we haven't created yet that'll be called setChunkPosition, that will set the position of this chunk to be equal to this vector2 ij, and we're going to add that chunk as a child of the chunks node. Next we want to start up our thread. This thread process function we haven't created yet, and when you start threads it expects to have some data being put in. That's unnecessary for us, so we're just setting that to be equal to null. Now we have to define our thread process function. Again, by default it expects some data to be put in. That's why I put this underscore in front of user data to show that we're not actually going to use that. We're going to continuously loop in here, so we're just going to have an infinite while loop that'll end when the program ends. In here we are going to loop through all the children of the chunks node, that is to say all the chunks. We're going to get the chunk position. You can see here it's a bit confusing that we're taking chunk position.x to be equal to x and then chunk position.y to be equal to cz, and this is just because chunk position is a 2D vector, but we're working in a 3D space. So we're mapping that y coordinate to be z because it's a 2D vector in the xz plane. Next we're going to grab the chunk position of the player. We're going to do this by taking the player's coordinates, dividing them by the relative size of a chunk, and then we're going to floor it so that it's an int, so that we don't have the player existing at 0.5 of a chunk. Now we're going to define the new position that the chunk should move to if it is outside of the load radius around the player. So how we're going to do that is we take the chunk, we're going to subtract from its position the player's position plus half of the load radius. We're going to use the modulo function, the positive modulo function specifically, of this divided by the load radius. Then we're going to add back in that offset that we subtracted earlier. Then we do that similarly for the z direction. Now if this new xz coordinate is not equal to the original xz coordinate of the chunk, we know that the chunk has to be moved. So we're going to call that setChunkPosition method again to set its new position. We are casting these into ints again so that we don't have it existing at 0.5 of a chunk. Then we are going to call the generate function on the chunk again so that it regenerates its terrain, and then we're going to update the mesh. Now we go back to our chunk script where we are going to add in that chunk position variable that we were just using. So here at the top of the script, we're going to copy paste in a chunk position, which will start as an empty vector2, and it's going to have a setter function called setChunkPosition, which we're going to put at the bottom of our script. This will take in a position, and in this method we're going to update that chunk position variable that we just created, and we're going to update the translation of the chunk. So again, you can see we're converting from a two-dimensional vector to 3 dimensions, and then we're multiplying that by the size of a chunk so that none of the chunks are overlapping. One additional thing we're going to change in here is that if we look at our world script, we can see that we're changing the chunk position, then we're regenerating the terrain, then we're updating the mesh. So while it's busy calling these two methods, the chunk is now in a new position, but it has the same appearance that it had before moving, which would look really weird. So we're going to make it briefly invisible after the chunk position has been changed, and only when the update method is finished being called are we going to make it visible again, so that we don't see it while it's moving and reloading. With that in place, if we run the game, you can see we are now in a field of chunks that are slowly loading in. As we go in one direction, chunks load in front of us and disappear behind us. And since it is being done on a separate thread from the player's movement, we can see there isn't really any lag. Now that the chunk management is in place, we can start up with some pretty basic terrain generation. So we're going to use open simplex noise to achieve this. So we're going to make a new open simplex noise object in the chunk code, and we're going to use that here in the generate function so that our map looks a bit better. So first, for each individual chunk, we're going to want to get its global XY or XZ rather position. So I'm going to call this global position. This is going to take first the chunk position of its parent chunk, which of course we're going to multiply by the size of a chunk, and then we're going to grab the IK position and add it to that, and that's going to give the XZ position specifically of this block, and we're going to use that value to sample from our open simplex noise, and the value that we're going to return from that is going to be a height, and that's going to be the height of the terrain at that location. So to sample, we use getNoise 2D v because we're passing in the global position vector 2. This gives us a value between -1 and 1. So we're going to add 1 so that it's now between 0 and 2, and then divide by 2 so that it is between 0 and 1. Now that it's normalized, we're going to multiply it by the Y size of a chunk so that it'll be a random height from the minimum chunk size to the maximum chunk size. Finally, we're going to cast this to an int because we can't have half of a block. Now, instead of using these static 16 and 32 values, we're going to use the height value we just calculated. So for simplicity's sake, we're going to say if it's half of the height value, it's going to be stone. If it's less than the height value, it's going to be dirt. And if it's equal to the height value, it's going to be grass. With that in place, if we load into the game, we've now generated some hilly terrain to walk around. Now that the world generation is in place, we want to be able to interact with the world. To do this, we're going to go back to our player object, and we're going to add a raycast that's going to be a child of the camera. And this raycast will point forward, so that is in the negative Z direction, out of the player's face, and allow them to interact with a block. Remember to enable raycasts. They are disabled by default in Godot for some reason. Next, to show which block is currently being pointed at, we're going to add a mesh instance as a child of the player. We're going to call this block outline, which, as the name suggests, is going to highlight a block. We're going to make it a cube mesh, and we're going to resize it to be just slightly larger than a block is. So I'm using 1.01. This way it'll perfectly engulf the block that it's being pointed at. For the material, we'll just do a simple new spatial material. For the albedo, we will make it yellow and slightly transparent, or very transparent rather. Make sure to turn the transparency flag on. So now the block that we're going to be looking at, we're going to put this block on top of it so it's highlighted yellow. Now in the player script, we're going to want to grab the raycast, as well as the block outline. We are also going to create some signals that we're going to use for placing and breaking blocks. So when the player tries to place a block, the place block signal will be called with a position and the new block type. Similarly, for breaking a block, we just need a position. If we go down now to the physics process function, we are going to add in the raycast logic. So if the raycast is colliding, we are going to grab the surface normal of the surface that it's colliding with, and we are going to grab a position. This is the position of the block that it's colliding with. You see, we're going to use the collision point, but this is going to be on the surface of the block, so we're then going to take half a step into the block. Next, we want to calculate the position of the block that's being highlighted using these values. So we get its x, y, and z coordinates. This is going to be that position value. We're going to floor it first so that it's now an integer value, and then we're going to add half. This is half the width of the block, which is going to bring us right to the center of the block. Then we subtract the player's position, because this is a global position. We're going to subtract the player's position because we're going to use this to set the translation of the block outline. Since the block outline is a child of the player, it's going to have the player's global translation already on it. That's why we subtract it up here. And of course, if we are pointed at a block, we're going to want the block outline to be visible. And if we are not colliding with a block, we want it not to be visible. Finally, in here, we're going to add the input tracking for the break and place buttons. So if break is being pressed, we're going to emit the break block signal. If place is being pressed, we're going to emit the place block signal. For breaking a block, we just give it the block position that's being highlighted. When we place a block, however, we take that block position and we move outwards along the normal vector to the surface of the block. So instead of placing a block at the block we're highlighting, we're placing it on the surface above the block that we're highlighting. So that's why this is there, and that's going to be it for our player code. Now we want to go to our world script, where we are going to listen for these block breaking and placing inputs. So up here in ready, we're going to want to connect on to those signals. So here we are listening for the place block signal. We will call a function in the world. That function will be on player place block. For breaking blocks, we will do on player break block. So we'll now add these in down here. First, for placing the block, we're going to want to grab from the position of the relevant chunk. So we take this position, we divide it by the size of a chunk, and then we floor it, we make it an integer, because the chunks only have integer positions, can't have it halfway through another chunk. And then we grab the block position, which we do as the remainder of division, essentially, from what was being calculated up here. with these values, we first get the chunk that the block is going to belong to. We're going to call a getChunk method that doesn't exist yet, but will in a second. If that chunk is not equal to null, we're going to update the block's data in that chunk at the bx, by, bz coordinate of the block, and we're going to set it equal to the type that's been passed in. Once that's done, we update the mesh. Now we just need to create the getChunk method. I'm going to do this really quick and dirty. It's pretty terrible if you really think about it, but we're going to loop through every single chunk, check all their positions. If we find one that has the same position as this chunk position, we're just going to return that. You could probably make this faster, maybe save all the chunks in a data structure where you can look them up by their chunk positions, something like a dictionary, but since we're almost at the finish line, we're going to use this rather inefficient approach because now there is only one function left for us to complete, which is the onPlayer break block function. Luckily, breaking a block is exactly the same as placing a block, just an error block. But now, if we run the program, we're now in our generated world. If we go up to a block, we can left click and start digging. And if we right click, we place stone blocks by default. There's a lot you can do to expand upon this. The terrain generation can be modified to have things like trees or caves spawn in. You could also make an inventory system for changing what block type you're placing, because as we can see here, when we're emitting the place block signal, we're just giving it stone as our block of choice, but you could very easily modify that so the player can place whatever they want. Here's just some footage of some other projects I've made using this voxel generation, just different types of terrain generation I've tried out. If you've made it this far, thanks a lot for watching the tutorial. I hope it was helpful. If there was anything that you think could have been done differently, please feel free to let me know in the comments. Like the video if you thought it was helpful, and consider subscribing for more coding stuff. I guess. I guess that's what I do.